right, this is Tuesday, which means it's time for another coding challenge. Let's see if everything works fine. This stream is for entertainment purposes only, and let's see what we got today. Yeah, is it still working? Yeah, looks like that. All right. So let's select a problem, and today it's what? No, again hard. I'm tired of hard problems. Why not just easy, and one more time, easy problems. Always hard problems. All right, so let's at least try to read it and maybe quote some if else thing. You're given an undirected graph, the original graph, with n nodes labeled from 0 to n minus 1. Okay. You decide to subdivide each edge in the graph into a chain of nodes with the numbers of new nodes varying between each edge. The graph is given as 2D array of edges where edge I is from some node U to node V and some cnti. Okay, it's an edge between UV and cnti is the total number of new nodes that you will subdivide the edge into. Now that cnti0 means you will not subdivide the edge. Okay, so we will be basically given already how many divisions we need to do. To subdivide the edge, replace it with cnt plus 1 new edges. All right. Yeah, that's why it makes sense. So if cnt0, then you just keeps the original edge. And cnti, new nodes. The new node are x1, x2, xcnti, and the new edges are okay. In this graph, you want to know how many nodes are reachable from node 0. Where a node is reachable if the distance is maxMoves or less. Yeah, it doesn't sound like a good problem to solve. It's like I'm reading already what, like half a letter sized sheet of paper, right? So it's and there's still no key idea what the problem is. So you're given the original graph and you know how much subnodes you might have. Given the original graphs and maxMoves, return the number of nodes that are reachable from node 0 in the graph. And why you need numbers, I just wonder. I mean, what's special about those numbers? Node 0, where a node is reachable if the distance is maxMoves or less. They're not reachable from node in the graph. Edges. All right, so 0, 1, 2. So 0 to 1 can be split to 10 nodes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 2, and this is 1, right? So from node 0, maxMove 6. So how many nodes are reachable? Output 13. So we can reach, let's say, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's already 6 nodes. And 1, 2, 3, 4, 5, 6. 6 nodes, right? So we jump from here, here, here. here, 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 and here. I don't really understand what are these numbers for. Why we need numbers here? I don't understand. Yeah, these three are not reachable, right? It's super straightforward. It's basically you do breadth first search from node 0 until you hit the limit on the number of iterations, like on the depth, right? So yeah, I mean, straightforward linear problem, linear complexity problem. I don't understand why it's hard. And I don't really understand what's the point of these things to be shown as CNT. I don't understand. I have no idea. Like how many nodes in the middle you might have. This is weird, but whatever. Examples: two edges 0, 1, 4, 1, 2, 6, 0, 2, 0, 3, max move 10, and equal to 4. All right, so let's also read the constraints. There are no multiple edges in the graph, meaning that two nodes are always connected with one edge. cnti is something between 0 to 1,000, to 10,000. Max moves from 0 to 10 billion. And from 1 to 3,000. All right. So for every edge, u is always less than vi, and u is greater or equal to 0, which is obviously it can be 0, and is less than n. Right? Okay. All right. Edges length is from 0 to minimum n times n minus 1 to 10 to the, all right, so there can be many edges. That's I got it. Mm-hmm. All right, so it's more like, I guess, implementation specific thing that makes this problem a little bit hard to solve. Yeah, because if I just convert all these intermediate things to nodes and these to edges, like these things have neighbors like this, like this, like this, so it will probably be too hard for memory. But we can do breadth first search even without this one, actually. We don't need it. All we need is let's see. Okay, let's switch to the whiteboard and go through the example 2 quickly. So we have what? We have 0, 1, 2, and 3. So 4 nodes, right? All right. So we have, this is 0. Let's say this is 1, 2, and 3. I'm not sure if it's fun way to connect them like this. Okay, 0 to 1 with 4. right? All right. 1 to 2, 0 to 2, and 1 to 3. All right, nice. There is no edge like 2 to 3. Okay. All right, so 1 to 2 is 6. 0 to 2 is 8. And 1 to 3 is 1. Extra node in between, right? And we have maxMove equal 10, right? So then n should be 4 nodes. No, n 4 meaning there are 4 nodes. Yes, we already see it from the edges. It doesn't. I don't understand why you need n to be from. It's already included in your edges. But okay, so the output is 23, right? Obviously, we may go this way, right? So it takes 5 to reach node 1, and we still have one more, it's 6. Then if we go 5, then the one here, we won't be able to reach the last one here and these two. So this is 5 plus 6, 11, right? And this one, obviously 0 itself is 12, then 8, 20, 21, 8, 9, 21. This is 9, and then I think like it should be 22. Oh, no. So 4, 5, 6, 7. 7 this way, 5, 5 this way, so it's 12, 13, 21, 22, 23. Yeah, makes sense. Um, So the thing is, for every node here, we want to find the depth, right? First. And so here the depth is, so it's if it's 0 here, so it's 1, 2, 3, 4, it's 5, right? It's basically 1 plus whatever we have here, cnt, so it will be cnt plus 1 in this case. This is the depth of the node if it starts from 0. If it's somewhere else, right, then it, and this can be done in breadth first search, BFS, to estimate depth, to estimate depth, all right, of key nodes. And key nodes are those with numbers of key nodes. So once we have that, all right, so this is 5. Let me put it in different colors so we can clearly see it. Let's say green, right? So this is 0, this is 5, this will be 9, and the only way we connect to 3 is through 1, which means 5 plus 2, so it should be 7. This is depth. So we already know that if let's say when we go to this node, right? If its depth exceeds the maximum step, uh, the problem is with such thing that let's say we have edge here, right? 2. Why not? So in this case, actually, the depth of this node can be either through node 1 or through node 2, right? And it will be the minimum. Let's say this is 0, right? So it's one hop, but this is 9. So in this case, it's 10. In this case, it's 5. And given the number of edges, it should be definitely linear thing. But basically, all we need is cover everything once, right? So let's say we go to this, we take this edge. If we cover it fully, we add the entire amount to this thing. Then let's say we go to this edge. We go through this edge. If it starts at 0, we add entire amount to this one and say that this number now has some depth to it. So next time we go through the edge like this, we know how many nodes can be covered, right? The problem is if it's, say, 8, 9, we can cover 1 node here and 6 nodes here, right? We might want something to check if they intersect with each other, like how many for the given edge, how many these tiny nodes were covered, right? And to this end, we might have some sort of a map to say from 1 to 3, let's say to the pair of integers, right? From 1 to 3, we have 6 nodes covered. So opposite way, we will know how many unique nodes can be covered. That's all we care. We don't care about finding the path or anything like that, right? If we can cover, we will. And if node was visited once, we don't need to revisit it again, even if it can be discovered one more time through another loop or anything like that. We don't really care. Unless through another loop, let's say we go the longer path here first, right? And then there is some other node, so we can cover only half. But let's say through this one, we can cover the entire node. So we do label correcting once we go, right? So if we see this node was covered and its depth this, but current depth can be minimized based on the prior node from which we traverse this new node, then we minimize it, and then if it's still not violate, we go to the next one. So how would we do this? Well, I would imagine we need some sort of structure. Let's switch back to the default scene. Where we have int, right? Say tiny n, whatever. And Oh, let's call not neighbors, but just an age. Whatever it is. So now, first, we want to create or do we want to make it as a map just inside the reachable node so we know the neighbors for everything? Yeah, why not? Why not? But then, ah, so the edge itself is a vector of int of 3 values, right? So let's say, nah, they're not, there won't be unique ones, right? It should be basically a vector of integers. So we add these edges. All right. Cool. Technically, all we care is just unique edge indices, right? That's all we need because we always have edges here. Nice. So let's first init nodes. Init nodes in or n. So what do we do? So basically for const auto, whatever we have here. No. I don't think we need it. We should just go with int I with 0, I less than edges size, I plus plus. Although we were given n, technically speaking, so we can create basically nodes of of n, right? And then for every edge, we do what? We say, but do we really need n here, right? We know that it's just basically this set of indices or whatever we want to have. So, so then we say, so for every edge we have 3 elements, right? So int source is edges 0. No, sorry, edges I is 0, right? Destination, yeah, we don't need cnti this time. It's 1. That's what we say. So we say that what? That node source insert I and nodes destination insert I. And here we need technically int steps, like or the whatever label, it's how many hops it's needed to reach it, right? And we can say by default, let's say it's equals to int max, right? So every time we find the better number of steps we can reach the node, we say it's what? Do we go back and forth? That's the thing. We only revisit node if we can improve its label. That's my feeling. So that's we can add more nodes that were not added. So the only problem is now how to track these intermediate nodes, which one were covered. But here we go. So now we create the queue of of node called queue. Then we also say here that node 0, the start one, it should be, let's say, edge indices right here. Steps equal to 0, because for node 0 we don't need any steps. So if maxMoves is 0, then should be 1, I would imagine. So that's what we do. While so Q, is it insert, push, or I would say push, most likely push. We push to the queue. Not 0, right? So because we start from not 0, while let's say unordered set, which will be int, and we call it unique nodes. Should we have just strings here so we can do something in 0, and then if something intermediate pops up, then we can say 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, such that we go the backwards. We always know that that might be interesting, although it will be a little bit more memory intensive, but yeah, heck, let's do this. Unique node names. Let's trick the system. Hopefully. While queue empty, not Yoda style, we do what? Very easy. All right. So should we have node as the reference, maybe? So that a pointer, whatever, right? So we have queue of pointers, so we push this thing. Right, basically reference to it. So node n, we use that. So next equal to q front, if I remember correctly, and then we do q pop, right? So now we need to go through all neighbors. Go through neighbors. Go through neighbors. So how do we do this? We do this simply by f int edge E in next edge indices. Should we just have E indices here so it's not too long? Indices, right? So we say node neighbor. We can say pointer to it is equal to what? Gee, I see. I see what's missing. Really, we don't know the index of the node itself, right? So we still should have its value. Int val. So it's basically straightforward. So we just say source, a node source val equals to source, right? And similarly for the destination, it equals to destination. So now we know, at least. So what do we say? We say edges I, let's say 0 equals to next val, like this, right? If it's this, then this is the source. Otherwise, it's the destination. But we don't really care. So whatever. If it's next val, then we need what? Then it nodes. Oh gee. One, and it should be like this. Otherwise, this is the reference to 0. Right. So here we quickly retrieve, or at least I hope that it's quickly retrieve the neighbor. I go through neighbors. So then we need to check one thing. So then we say nh, right? Steps should be steps is the mean between what? Between next steps plus whatever here edges I, this will be 2, right? It's cnt, and I remember it should be cnt plus 1 to be specific. And nh steps. So we keep whatever is minimum, right? Or I see, yes. So we don't usually care if we hit the same node, let's say the same neighbor through some other nodes, and the number of steps we hit it is larger than the prior one. So in this case, we don't care. right? So that's all we say if this thing is actually less than steps, right? Than the current steps. Then we don't need this check. Then we can just directly assign this number. So now, so let's see. Let's once we pop this next, let's also unique node names. Insert what? Insert let's say n plus next value, right? So it's there. Now, we don't need to insert neighbor here into this thing, but we do need to check one thing. So if steps less than max moves, less or equal than max moves, we add it to the queue. Right? And then we should mark, and despite that fact, if it's less or not, if, right, so, oops, okay, not that bad. If those steps less or equal max moves, we say queue push nh, right? We basically add it. And then we need to add intermediate nodes to unique. So what do we do basically? We go for int, what it will be, 0, cnti, I guess. And let's say j equals to 0, j less than edges. Oh, we're almost run out of time, but I guess the logic is here. So just a few more minutes and we're done. So all we need is just to create the unique name. So let's say the name always starts with edge I0, then edge 1, and then cnt as we go. So the only thing we need to decide from, do we go from the end of the edge, right? So how do we do this? I see. So basically we say for yeah, they told us that there is a specific direction, right? That u is always less than v, so we don't really care technically. That we know that in age is always increasing, but whatever. Let's assume there's no such thing. It doesn't give us a lot of benefits in terms of complexity. Anyway, let's just say bool next to an age, And this is equal to what? If edges equals to this thing, right? And actually we can move it here next to an h. So we start from 0 and go into an h. So this is h, this traverse way, or we can go maybe from larger integer to lower integer. So it will be reverse one. So then we can say just next to an h, because it's the same check here, right? And then an h is the 1, otherwise it's 0. It makes sense. So what do we do here? We say that that we depends on, okay, let's keep this one. Should it be, because 0 is the in h itself, so this is will be the 1, so it's the first step, right? So it's 1, and cnt is included in this case. So we say only this thing. So it really only affects the name, technically, if next steps plus j, right, less or equal max moves, we insert what? We insert, let's say, this way or this way. No, we always insert, let's say, in this order, right? So it's from, we don't need n technically in this case, edge 0 to edge 1, and plus some underscore plus, and now we need to understand, do we subtract the j index from this one or not? So if we're moving, so from next to nh, right, meaning that it's the source, so meaning that the nh index is larger than this one, then it's a direct traversal. Then we just should say it's probably next to an h. Where is this thing? Next to an h, where is this thing? Okay, next to an h, then j, otherwise. So if j is 1, and let's say the last cnt is 4, right? So it's 1, 2, 3, 4. So then we start with then it will be, because j is 1, then it will be edges 1, 2 minus j plus 1 minus j, right, plus 1. So the j is 1, it cancels out with 1. So if j is equal to this, it will be first element. Yes, make sense. So now let's, oops. Right, so I guess we're actually running out of time. So let's just debug it, all corner cases and stuff like that, and we stop here in terms of logic, right? So all things left to do, so we insert next and each step, right? Only if we can reach this node with some nodes. If not, then whatever here we insert, if possible. If steps already equal to max moves, that we won't be able to insert any unique names here, which is fine. So once this is done, and this is done, then we go here, the while cycle is empty, and then we return unique node name size. So the first one will always add 0, right? Where's this thing? Yeah, we always insert this element because we only add next major node, the key node, if our distance allows us to do this, right? So we say if max moves, if less or equal than max move, then we push it to the queue. Otherwise, we don't touch it. And add intermediate nodes here. So every time we retraverse current nodes, we just, set will tell us, okay, this node is already there. And key nodes will be n something value, whereas non-key nodes will be always lower index to higher index, right? And subscription will be what? Either J, so either direct traversal or reverse traversal. Let's see if it compiles. Most likely not. And then we will see how to debug it. Oh, yeah. Sorry. So we used steps, we used val. All right. I always use node on instead of nodes. I'm just curious. Edges, 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 edges. Or no? Is there any? Yeah, let's just run and see. Adding into a string doesn't append to the string. Right, let's go with this. CPP, append into string. So how do we do this? Str to int. No, not through this thing. To string, okay. This is better. I like it. Let's just do to string. Then I guess we don't really need. So in Java, here is the hook, right? And the trick, you can actually just add plus between int and whatever, and the int number will be between string and whatever thing, and in most cases will be converted. But all we can do is just say this, right? So I don't really care here, and we do need this for these things here, right? And here, so we close brackets, just a little of debugging. It doesn't really change the logic or anything like that. It's just string J, or this thing was already to string, so we don't need this one. Right, correct. Or no, wait a second. This is this. This is to string, so yeah, correct. Run the code and see if it compiles now and runs. No? Oh. Yeah, this is unfortunate. So what's about it? From basic string to bool. We don't need this stuff, and it's actually just to increment, basically add string here, right? So one more thing. Right, should work now, hopefully. All right, it's infinite loop, output 1. Oh my God. Why? Why this happens all the time? Let's just see out. See out. Let's say n is of what, of next while here, right? Steps next steps. I guess it should be this way. Of course. All right. Let's then see out also intermediate nodes here to see if we can redo this thing. Basically, let's, you know what, let's just do next wall. We don't need this one, right? Because we know, or we can say name, oh, come on. The name and then, seriously, steps, name steps. And yeah, basically that's all we need. So we can just reuse it here. So the steps will be this. It's like intermediates, right? And the name is, gosh, is this. So yeah, whatever. It's out, it's okay. I would imagine. All right, so let's see. Run the code if you get anything at all. Name 2, step 0. Interesting. Let's also print here neighbors something. I have a feeling that neighbor size, which is next e wherever so wait a second, what's this? It's okay. Next e indices size. Does it mean we haven't inserted really the neighbors here? It should be I, so it should be those edges here. So I don't know. Let's see. Run the code. An H size too, which is correct. All right, so let's see for this guy, right? Before adding to the queue, a name, an age, and in age. Something is weird here. No. Mm-mm. So, but in each steps. All right, so let's do this thing then. So we know that it never enters this internal if, right? So let's see what the inage is and why the steps number is always larger than this guy. It just doesn't make sense to me, honestly. Stupid. It should enter this internal if. Oh, wait a sec. Why on earth? Let's call it n here. First of all, I don't understand why it's n equals to 2. It should be 0, not 2. Did I miss something? Source. Ah. All right. So if 0 equals to wall, right, so maybe now this will work. Let's see. It's still 12. Curious though. So yeah, we go. Yeah, I think we don't need this anymore. So we can just comment it out, run it, and see. So it should start with 0, then it go to 1 and 2, right? Well, we don't start with 0, which is weird. Oh, okay, not this one, the wrong one. This one. Because we have 1 here, right? Run the code. Right, so is our logic. So we start with 0, step 0, obviously, so it's 1. So now we go to name to 2, 1. And we had only one intermediate node there, right? So it's clear that steps needed to reach it is 1 step, so we added, right? Then we also added node 1, where we have 1, 2, 3, 4, 5, 6, because we have from 0 to 1 we have 10 actually, but we have max steps of 6. So yeah, so the 6 is the last one. So we add it here, right? So we already have 1, 2, 3, 4, 5, 6, 7, 8. So now obviously we add what? We add node 2, right? So these been added to the unique names as well. So it's 2. And then we say from 2, because we traverse it, it was from 0 to 2, right? From 2, we go to, so 2 has what? Neighbors of 0 and 1, right? We reach it in 2, so it's 9. Then we go 10, 11, 12, right? And then we stop at N1. Interesting. Yeah, we won't go to the next node if its steps are no lower to the next key node if the steps are no lower than that. Ah, I see why. Yes, exactly. But I mean, technically, because we say only this thing, right? So yeah, I think all we need to do is basically mean this thing and in each steps and remove this completely. I think it will solve the issue. Because what happens is because we can't go to one through the node two because it's too far now, right? We don't check these intermediate nodes that can be covered. That's the problem. Technically now we need to move it here. Whatever, I won't move these things. Too complicated. Too much of time needed. Right. So what do we do basically now? We just take the minimum number of steps and then we check if the steps is less than max move, then we go. All right. We don't need to check the max moves only, but we also need to check if the steps have changed, right? So maybe we still want this. All right, check. So if we improve this, let's do this. Let's say bool can improve, can improve steps equal this thing, all right? So we don't need this guy now. Sorry, no, we need this guy. We just say less than in each steps, right? And then we don't obviously need this. We can say can improve steps. Then next steps was fine, otherwise this, which is obvious. And now, if NH steps were improved, and we say if we can improve steps and NH steps is less than max move, then we push it to the MQ, and then we check these guys and add them to the queue every time. So we don't go through key nodes twice, unless we can improve the distance and cover more nodes. Let's see if this now works and returns 13 as it should. And accept it. Yes, now it works. So yeah, just a reminder, despite the fact that 40 minutes passed, we're technically not solving the problem now. We're just debugging it and covering corner cases. So I would say for hard problems, it's okay. So yeah, let's just see if, so let me see, run code, then nothing is printed out, and we will submit and see if it works, if it passes. So this, by the way, because we traverse every unique node almost basically only once, unless we can improve the distance, which might be the case or might not be the case. The rest is hard to say if we can improve it or not, but whatever, let's see if it's, so my suspicion is still linear and it should pass the check, but maybe not. Maybe we'll get time limit exceeded as usual for hard problems. Yeah, okay, whatever. So this, because we can redo some traversals, we still cannot fix linear. So I guess the key here is really to try to get this benefit of having how many nodes up front, right? We have, and having the fact that edges are from 0 to 1, from 1 to 2, from 3 to 4, and maybe try to see based on the count. Maybe you can push this to the priority queue based on the count and check somehow, whatever. So it seems like more complicated logic is needed than just regular breadth first search traversal. But we passed 38 out of 47 tests, which is fine, I guess, for the hard problem. At least we solved it, right? So the code is working. It's near linear, my suspicion. Maybe not near linear, maybe more. So let's go and just update the, yeah, again, 0, but that's okay. So it's 30, 30, what, 39? 38 out of 47, okay. Yeah, never know with these hard problems. You feel like it can be a good solution, but sometimes it passes, sometimes it doesn't. All right. Thanks, everyone. See you tomorrow.